Hi, my name is Serenay Elmas. I'm a member of Structures and Architecture Unit, which is a group of multidisciplinary researchers at Aalto University focusing on geometry and lightweight structures. Within my PhD studies, I have been particularly working on the utilization of elastic torsion as a design driver for structures and architecture. Today, on behalf of all the co-authors of the paper, specifically Professor Günther Filz, Dr. Athanasios A, and Professor Jani Romano, I will be presenting the structural geometry of a beam element which is assembled from 4 thin elastically taut strips. Here you could see the concept for the shape generation of the proposed beam element. As shown, one can easily achieve the geometry in 2 steps. Firstly, by repetitively folding a rectangular sheet of paper 3 times to achieve a tube of square cross-sectional shape. Secondly, by crosswisely connecting tube's short edges to obtain 1 degree of freedom mechanism. So the beam generates a self-restraining system which relies on the deformation of the individual paper segments. Accordingly, the linear edge lines of the strips transform into planarly curved seam lines. Besides the twist of 90 degrees, a simultaneous sideways shift of each of the 4 strips occurs. Consequently, both elastic torsion and elastic bending are under 2 different axes, considerably influences the final geometry and inherited stresses in the material. Differently from the paper models, the full-scale beam element is assembled from separate strips by means of a lacing technique which doesn't necessitate nuts, so it provides quick closing, adjusting, and reopening. The strips were cut from 6.5 mm birch plywood sheet material. We use 6 elastically taut beam elements as horizontally cantilevering beams for the roof of our realized kinematic pavilion, Zero Gravity, in 2019. Even though the beam can be used and combined in many other ways, this was the first validation of application in full scale. In addition to the physical prototypes in various scales, our investigations are including computational structural simulations for the digital generation of the shape, as well as geometrical and structural analysis during the formation process. The comparison between digital and physical prototypes is based on photogrammetric reconstruction, where the results show highly precise matches. We tested the beam element against bending, and as a result, the point load applied in the cantilever's free end has been 25 times beam self-weight, which was quite promising. On the other hand, one of the most interesting observations from physical models is the emerged undulating surface of each strips, which was initially perceived and thought as an imperfection of model making, but instead it was a result of the self-equilibration of the structure. Observed phenomenon is related to what has been described by Föppl-von Kármán equations in terms of stress resultant. In relation to that, activated geometric stiffening effect is associated with very thin material thickness and considerably large deformation as a natural consequence of the proposed formation process. As our preliminary results indicate, depending on the achieved equilibrium states, the resulting geometry could provide super lightweight, yet highly efficient structures with compelling architectural and functional features. We are continuing our studies to exploit further geometric potential of the formation process by changing the cutting pattern of the strips, the angle of induced torsion, and so on. For all the other aspects, I will be happy if you could read the full paper and contact me for further discussions. Any email or contact is very much appreciated. Thanks for attending.